Hello, my name is Rafael Garcia, and it is my great pleasure to be here and talk to you about the challenges of vision-based robotic ocean exploration. I would really like to thank the organizers for giving me the opportunity to give this keynote talk, and I hope I can entertain you for the next 30 minutes or so, presenting the work that my team and myself have been doing in the field of underwater vision. So let's start the talk by asking what is the main objective of our institute, the Computer Vision and Robotics Institute of the University of Girona. Basically, we develop technologies for the exploration of the ocean. And how do we do this? The way we do it is we develop robots that are equipped with cameras, and the robots have the ability to navigate in a very controlled way and get very close to the seabed. And in this way, as they are equipped with cameras, we can collect images and then use these images to process the signal and be able to control the robot and take decisions. But using vision underwater is a challenging task. Basically, as you see here, we have absorption problems because the light as an electromagnetic wave gets absorbed as it penetrates the water. Basically, the energy of the light, the energy that it's being lost is being converted basically into heat. So it disappears from the imaging forming system. We also have problems of scattering, which means that the light is traveling in a straight line, but then it might find a particle in the water and then change direction. And then this change in the direction can be either backscatter if it changes in that direction and then goes to the camera, or if it just changes a small angle, then it's called forward scattering, a small angle forward scattering. And this is generating blurring in the image, which means that the contours are not so well defined, especially if the path that the light needs to travel along water is longer. And many times we need to add light to the system because the natural light is not reaching the scene that we want to picture, and or some of these wavelengths might not reach it, and we need to add artificial light, and then this normally generates some sort of non-uniform illumination. And apart from this, as you see here, we need to get very close to the seabed to be able to gather data, and then this means that data collection is quite expensive and quite time-consuming. So there are several challenges. Let's have a look at some examples. Here you have an example of an image. In this case, is an underwater archaeological site, and you see that the part of the image that it's close to the camera allows us to distinguish some of the features of what appears in this archaeological site. But if we look farther away, you see that in this area, we have very poor visibility. We don't, as the light needs to travel farther and farther, we are losing this signal. And you see in this case that we are seeing white when we are looking far away. Let's have a look at how this process is happening. So here we have an example of an object, and then the camera that it's capturing the radiance that comes from this object. And you see that here, as the light goes from the object to the camera, the thickness of this red signal is thinner and thinner. Why? Because we are losing light because of absorption, as we said, and because of scattering. So part of this light is changing direction, and then it's not reaching the camera. And you see that what the camera is getting is a small fraction of the original radiance that was reflected by the object. Okay? But according to what we saw before, if the object is very far away, we have seen that we were seeing white. Let's go back to the previous image. You see that it's brighter when it's farther away. And according to this model that I'm showing you, it should be darker because I'm getting less light. And if I get less light, the image should be darker. Why is this happening? In this case, this is happening because we are in shallow water. And what happens in shallow water? In shallow water, I not only have the radiance of the object times the transmission, which is a factor. This dx is a transmission. But we also have the light coming from the ambient light, from the sun. And this is called Weiling light in this context. And this Weiling light is basically contributing or adding to this red signal, because part of this blue light is being scattered, and it gets scattered along the same direction of the given pixel I'm analyzing at this time. And this is why the image gets brighter. It's because of the Weiling light. What I want to do when I process images underwater is to get rid of the blue component and try to recover the red component, the object radiance. Okay? So basically, what I get in my image is not Jx times Tx, but I get the radiance times the transmission plus this air light times another factor, that it's 1 minus the transmission factor. Okay, so this is weighted. Depending on the water body, these two weights are going to give more weight to J, to the radiance, or it's going to give more weight to A, which is the air light, this Weiling light that you see here. So our task in underwater imaging is trying to recover the red signal and get rid of this blue signal. Then, as I said, this is a situation in which we were in shallow waters, and in shallow waters still we have other problems, like this flickering caustic pattern, which is because of the surface of the water, the rays of light that are coming from the sun are being reflected, changing direction because of the surface of the water, and in this change of medium from air to water, some of these rays concentrate in a given area and then provide bright spots, and they disappear from other areas where they should be lighting, and then generate other areas that are darker, okay? And this is an example of what happens, in which if I try to apply normal computer vision techniques here, I'm going to recover the motion of the flicken pattern and not the motion of the robot, which is what I want to do. So this means that when we deal with underwater, we need to take into account if I'm in shallow waters or I'm in a place in which I have this flickering pattern, or the type of pre-processing that I'm going to need. It's going to be slightly different depending on what situation I am. And here, again, we are just 67 meters depth on a lake in Lake Michigan. And you see that here, when I look at the points that are farther away, I actually see dark because there's no light coming from there. But then I have my light switch on. And in the volume in which the light and the camera are sharing the same space, then I get light from the light source that it's backscattered to the camera again. And this is this effect that you see here of these white spots. This is called marine snow, and this is the backscatter that I need to deal with too. Let's see other examples of things that happen. This is another example in this case of our Sparrows robot, in which you see that when the Sparrows robot is in the air, you see it's a nice orange, but then depending on the day and depending on the water conditions, you see that it might not be that orange, and even it might be turning to yellow on some other day. And it's not because it's being chased by a diver, it's because of the characteristics of the water column and the particles that we have there. And then light is interacting in a different way depending on the wavelength of the light and the size of the particles that we have in the water. So somehow it has this chameleonic behavior in which colors shift depending on the day underwater. And then this is something that I should be taken into account. This is an example of our calibration pattern down at, you have the depth here, 1,696 meters depth. If I get a closer look of this, you see this is the original image, and this is the image we get when we correct the colors, trying to do this photometric calibration of the camera. You see, compared to the colors we should be getting, still we are okay, but some of the colors are still a bit off. And this is an example of the type of processing that we do when we are trying to get rid of the problem of caustic patterns as I told you, in which this is the original image, and then for this image, we compute a temporal medium, and then we take the difference between the current image and this temporal medium. We get two components, and one of these components is the illumination field that then we can remove from the original image and get the output image, which is the image that we're going to use to process if we want to build a map with this sequence, for instance. And sometimes building the temporal median is difficult, so we have been using also something that is called dynamic textures to predict what the pattern of the light should be in the next frame. And basically, this is an example of how you need to adapt to every specific conditions so that you can, in this case, you see the original image is used to learn the pattern and model how the next feature, the next image is going to have a light pattern, and then I can remove and get a better conditioned image for doing a map, for instance. And these are examples of how to do something that we call dehazing, which is basically getting the red signal out of the combination of the sun of the red and the blue signal, so that removing this veiling light that I told you. This is an example. You see that it seems that the visibility is quite improved, but when you compare this to the real chart, you see that all the reds, for instance, have been lost because we don't get this red signal, and then we are not able to recover. So this absorption that underwater images suffer from are basically wave dependent, and they depend a lot on the characteristics of every water body. And even in the same place, it can change from one day to another day. And this is an example of the same calibration pattern, the same color calibration pattern in our pool, in the Underwater Robotics Center. You have the original image here, and from this image, we are able to recover, to improve and enhance the visibility of the image to get something like this. If you have an ROV pilot that it's driving or piloting an ROV, the robot, you want him to have the maximum visibility. And even if we are not able to recover the true colors, we want to at least be able to distinguish things underwater. And this is another example, in this case, of two cannons out of a shipwreck in the coast of Toulon in France, in which the images that the archaeologists were using are not these ones here, but the enhanced images in which we can zoom in and see some of the features that they want to find there. And this is an example of a video that we took from the internet, in which you have on the left the original image, and on the right the dehazed image, in which we are trying to, as I told you, recover and maximize the contrast of the images, so that these are images that are better conditioned to be used later on if we want to analyze, if we want to detect objects, if we want to use them for building a map or whatever. You see that there are some color artifacts, like in the top part here, you saw a little bit of red that was being produced, but in the overall, basically, what we're trying here is trying to take into account that processing underwater images is a tough task, and we want to improve and maximize the quality of the images before we use them for something else. So in summary, you see that we have three different situations underwater. We have shallow waters first, and then there we have seen that we have problems of sun flicker, of turbidity, and then suspended particles might affect the way the images look like. Then we have the water column, in which you have always to use artificial lighting, and then you get backscatter, and then you have the deep waters, in which normally you have lack of contrast and loss of colors, and you always need artificial lighting that will generate and will cast shadows on the scene. Basically, when you light something and you light a 3D object, and then you move your robot with the camera and the light rigidly attached and you move to the right, then the shadow is going to be in the opposite direction, and it's going to generate like a motion flow that goes in the wrong direction compared to what you want to compute. Okay, so this is somehow a difficult situation. But the take-home message here is the following. If I just take images that suffer from this type of artifacts, and I try to align them, to register them, extracting features like shift, for instance, and then trying to compute a transformation that aligns the two images, this is not going to work out of the box as it works with terrestrial images. But the good news is that if I do a proper pre-processing of these images, or in this case, for instance, on the top example is equalization and some flicker removal, then the same shift method is going to be able to align the images. Then once our images have been properly pre-processed, we can start doing maps with the images that the robots are gathering. Basically, the idea of optical mapping is based on what you have here. This is not real speed, but it has been accelerated. And you see a robot that it's doing a given pattern, and this is a low-more pattern, it could be a different pattern, but basically there's a fundamental problem that we need to solve here, which is once we have pre-processed the images, we need to register them. And registering consecutive images is relatively easy. What is more difficult is to detect loops, which is basically when your robot is navigating in a given area and then does a trajectory and revisits the same position, the same place of the scene again, of the seabed again. And you want to recognize that you are in the same place, because as the robot is doing this trajectory, it's going to accumulate drift by estimating the individual motion. Even if you're using navigation data, if you're using DVL, you're using INS, you're going to accumulate drift. Then one of the things that we need to solve is to detect loop closures, to be able to re-estimate the trajectory and then reduce the drift that you have in the full trajectory. This is an illustration. You see in blue the trajectory that the robot is following, and in green the estimation that the robot, where the robot thinks it is. You see now it closed a loop, and by closing the loop, the robot is able to relocalize itself and have the uncertainty that it had the first time it visited that area, and now we can do a bundle adjustment or smooth the trajectory to get something like this, in which we have improved not only the current position, but the position of all the loop all around, all the trajectory that the robot has followed. In our case, we are solving this using visual back of words, which is an approach in which basically we describe images as a number of objects that are present, a histogram of objects, in fact, that are present in the image. But we do it by learning the vocabulary as the robot is moving in a given trajectory. And this is an example of, you see on the left the current image, and on the right the image that is being matched based on the current vocabulary that we have learned. And in this way, we are able to match images even if they are in different orientations, and because we're using words that are rotation invariant, and then this allows us to close these loops and re-estimate the trajectory of the robot. This is another example in which even if we pay a lot of attention to the pre-processing of the images in some situations, like in this dam inspection application here, it might not be enough, because you see when we build the map, this is what we get. You see, basically here you see very dark images and the seams between the different images. The places, because of lighting differences, where the images are being connected. In this case, this is an inspection of the wall of a dam. And you see that when we post-process these images, then all these new features appear, and I see these little plants that are growing here, and if there's a crack in the wall, I'm going to be able to detect it in a nice way. And this is the image I want to give the engineer to monitor the status of the dam. In this case, what we are doing basically, it's trying to apply a blending technique. You see, in this case, in the images, you see that because of the lighting differences, you see the seams, or where one image is finishing and when the next image in the map is being applied, forming this mosaic. When I do blending, basically I take these images, I go to the gradient domain, force the gradients in the seams to be 0, and then go back to the spatial domain, and what I get is something like this, in which you see that now I can concentrate on the objects that I have in the mosaic and not the seams in between the images. These are blending techniques that we apply to be able to have a better image, a better mosaic image than to be used to be further processed to detect objects applying machine learning, for instance, or any other application. This is an example of maps that we are building using third-party robots, in this case a robot from the University of Puerto Rico, and in this case this is a coral reef area that it's been mapped at a resolution of 1 millimeter per pixel because we want to classify the corals afterwards, and this is the resolution that we need for that. And you see down here, this is the footprint of an image, and you see how small footprint of an image is compared to the full map. And we are applying the same type of techniques, for instance, in the Mid-Atlantic Ridge, in the place where the tectonic plate of Europe and America meet together. For this, we use the ROV Victor 6000 by Ifremer, and out of the images that we collect there, we can build these nice maps. In this case, this is covering about 700 by 800 meters of the seabed at a resolution of 5 millimeters per pixel. And then we can place all these different maps. We can detect changes over time for explorations over the different years, and this allows us to characterize the seabed. And I can select a given area, and I can mark the venting areas in white, or the diffuse outflow, so the bacterial mats, the places where new bacterial patches are appearing, high temperature vents, inactive vents that had been there in the past but are not active now, and fossil discharge zones, for instance. And this is only possible if we can build these maps over time and then use a baseline map to compare and detect changes over time. Of course, we can do this with images in the Mid-Atlantic Ridge, but we can also do it with images like in this case of a coral reef, in which we classified the different corals in the photomosaic, or in this case in which we are applying classification of munitions, what it's called UXOs. In this case, it's not only using features that take into account the photometric characteristics of the munitions, but also the geometric characteristics, the shape of the shells are a feature that is used then to train a machine learning system that is able to detect them. So in this case, we're not using deep learning, we're using support vector machines, because normally they generalize much better when the amount of data that you have is much smaller. But when an underwater robot is exploring the ocean floor, we can only use these 2D mosaicing techniques that I just showed you when the seafloor is quite flat. If it's not flat, we need to move to other type of techniques, like structure from motion, in which we are using the cues and the information that we get from the images themselves to estimate what is the relief of the seabed. And normally we do this by combining then this information with other navigation data. Let's see some examples of how we are applying this in different techniques or in different application areas. This is an example of an hydrothermal chimney called Tour Eiffel in the Mid-Atlantic Ridge. You see here the depth that we have here is 1,680 meters. And from this type of images, we want to do all this pipeline of pre-processing and so on, and then use this information to get a 3D model of the hydrothermal chimney. In this case, we need to basically apply structure from motion, get a cloud of 3D points, densify this cloud of 3D points, get rid of the outliers. We need to apply specific techniques because we know we're working in underwater and we're going to have a lot more outliers, like which are these red points that you see here. Then we need to remove them because of this scattering and the light that is being reflected underwater. We need to develop specific techniques for 3D reconstruction underwater. And once we have done this, we can come up with a nice color-corrected 3D model like the one that you see here, in which then we can have a visual permanent record of what is the state of a given hydrothermal chimney at the time that we were doing this exploration. Then we can, of course, go back to the same area after a few years and build a second model and then analyze and compare, register the two models and then see if there have been some changes in this place or that place and how this is affecting all the life that is here and all the, basically the biology and the geology and so on. Because here, these are areas in which even if we are very, very deep in the ocean floor, we have mussels and we have basically creatures that have adapted themselves, like crabs, like shrimps, that have adapted themselves to live in these very extreme habitats. But you see how the detail that we can get from these models is very, very, is very high resolution. Okay? And then, of course, we can do the same in archaeology. This is an example of a collaboration with French archaeologists in which you see that we can recover the 3D model and then, of course, apply the texture onto that. And we have also been doing this with underwater archaeological center in Catalonia, in this case for the ship called Cap de Vol. Here you can see the 3D reconstruction of the shipwreck. In this case, we did this with very high resolution cameras. In this case, it was 12 megapixel cameras. And you see that the level of detail that you can get for this type of shipwreck is very high. In this case, the images are not color corrected. The color correction was carried out later on. But you can imagine that it's very different for an archaeologist to be able to use the 3D model as it gets out of a 3D reconstruction software after surveying it with an ROV or even with a camera itself by the archaeologists carrying a camera and then using photometric 3D reconstruction to get the 3D model. In this case, we're talking about a ship, as I told you, from the 1st century before Christ, that was about 15 meters long. And it's very interesting to be able to do all the analysis and the studies that the archaeologists need to do of the different parts of the ships by looking at the 3D model instead of using a lot of time being underwater and diving. And here you see an example of a ruler that was placed by the archaeologists that was 10 centimeters and the measurement that we get for the 3D model when we carry out this measurement. But I think it's a very good example of how technology can change the way in which some of these explorations are being carried out in nowadays underwater archaeology. You have to think that depending on the depth, the time that an archaeologist could spend underwater is very limited. If you can do this type of 3D reconstruction with robots, then basically you gather a lot of information in a very short period of time, and then you can use this information back in the office to analyze the different aspects that you want to analyze about the archaeological site. And you can, of course, edit it, carry out measurements, check how this compares to other artifacts that they have mapped before and so on. So it's a very interesting application. But then if we are exploring the ocean using an ROV, for instance, you know that the cameras that we have in the ROV, normally we have a camera that is looking forward and the pilot is using that camera to teleoperate the robot and try to explore the unknown ocean. And this is some sort of a tunnel view. How can we solve this issue of the tunnel view. One of the proposals that we do in our research group is to use this type of cameras. This is an omnidirectional camera that will allow us to explore in half a sphere. So to have a view all around us and under us, because we're going to locate the camera like this in our robot. Then we can have a thin tether, convert our AUV into a hybrid remotely operated vehicle, and have this immersive perception and explore the ocean like that. We also built a low-cost version of this camera based on GoPros that allows us to record omnidirectional data and then process it offline. And these are some examples of the type of images that we're getting. Here you have 5 images collected with this type of system. Then we can take this stream of images and place them using a spherical projection on a sphere, in fact, and with that we will have this omnidirectional view. But we have a problem here. The problem is that to get this equirectangular representation, basically here what you're seeing is this equirectangular image in which every column of the image is going to be a different angle, and then everything melts together into the nadir point, which is this bottom line here. Okay, so this is a planar representation of half a sphere that I'm using to put together all these images and generate this omnidirectional view of the scene. Here I didn't correct the colors of the different images for you to understand one of the fundamental problems that we have when we try to do this. And what we try to do basically is we are assuming that everything is at a sphere that it's at a given distance. So we have parallax issues. This means that objects that are closer and objects that are farther away are not represented or could not be represented in the same sphere. And here you see if I represent the sphere at 1 meter, you have the drum that you see here in the image marked with this red square, that it's not matching. Instead of 1 meter, I go to 2 meters, you see that the drum is aligning a little bit better. And at 5 meters, then it's aligning much better. So, but now the things that are closer, for instance, at 1 meter, this part was correctly aligned, but if I go to 2 meters, or if I move to 5 meters, then it starts to have inconsistencies, all right? Then what is the solution for that? One of the things that we propose is to compute, instead of assuming a spherical wall, to adapt the shape of the projection that we are doing, like using this type of potato, based on what we measure in the scene, so that we can use structure for motion as we move to compute what are the distances, what is closer and what is farther away, and then I can adapt to this. For doing this, we are basically using 2 approaches. One is an online approach, in which we have as a backbone a SLAM process that will allow us to get like a sparse representation, and then based on that we can have a rough idea of what is close and what is farther away. And then we have a second offline approach that will allow us to get a denser cloud of 3D points using structure for motion, and then we can do this for demonstration purposes if we want to show the model offline. This is an example of the type of key points, the sparse key points that we can detect in real time, several times per second, and then build a filtered depth map based on that, which is this representation that you have down here. And with this type of approach, you see that at different distances, like this 2 meter, with this online approach, I'm able to adjust for the drum and then get a better representation. And the same here for the object that it's closer, represented at 2 meters, and then represented with this alternative shape instead of using a sphere, okay? And this is the final image that we are getting, basically, with the offline approach and the image blending. But at the same time that we are collecting images and building these omnidirectional views, we can be processing this stream of images. Basically, the fact of having cameras looking all around makes this image acquisition process a lot more efficient, because I'm able to see all around my environment. And this is an example of a collaboration we have with the Australian National University, in which we are using the 5 cameras all around the robot to know what is the trajectory that the robot is following and what is the quality and the uncertainty in the 3D reconstruction of this sparse cloud of 3D points. And in this way, during the data acquisition, I could replan the trajectory of the robot and then go back and revisit exactly the same area. And this is a playback of the data that I have got. In this case, I can see the trajectory. And we see that just with a short survey, in this case, this survey was around 11 minutes. 11 minutes of survey around this shipwreck, which was about 40 meters long in the coast of Costa Brava here in Girona. We see that we can collect a huge amount of data. And then I can take this data and use it for offline 3D reconstruction. And you see here the type of 3D mapping that I can achieve based on that. And here there's an example also. This is the cloud of 3D points, and here I have the equirectangular image corresponding to this side of the boat with the stair, so for you to compare. Then, what are the benefits of using omnidirectional cameras? Basically, we have seen that I can have this feeling of immersion and telepresence and know what I have around the robot instead of having this tunnel view that normally ROV pilots have. Then I can gain spatial awareness, and then I can be more reactive in terms of the dangers that I might have on my surroundings. And this could allow me, as we have seen right now, that I can do online mapping, and then even I could know what parts of the map are correctly mapped, which ones need still to be revisited for having a better information in those regions. But then, if I have all these elements, why don't we go one step forward? And basically, the motivation for this is going to a situation in which the scientists can be taking the control, taking the joystick of the ROV. In this case, I don't need to be an expert pilot, basically, because since I have these omnidirectional cameras that have a view all around the robot, I can start assigning basically risk to depending on the distance at which I'm detecting the different points. This is an example getting inside of this shipwreck that I showed before, and you see in blue points that are far away and then are not dangerous, and in yellow points that are a little bit more dangerous. And you see here a good example of this. What you're seeing now is our simulator with Girona 500 on the left, and the environment that the robot is detecting on the right, and 6 omnidirectional cameras on the top part. And you see that here what we're doing is we are allowing an unexperienced pilot, it could be a scientist or it could be even a child, to take control of the robot. And basically the robot, as you see now, this force that the robot is doing, when the robot turns red, this means that the robot is not allowing the pilot to take control of the joystick, and it's acting on its own safety, acting to ensure the safety of the robot. And basically, we can use these omnidirectional cameras to avoid collisions, and this is especially relevant when you need to operate in confined spaces, when you are very close to the seafloor. And for this reason, to help with this problem, we have envisioned a system based on this omnidirectional vision system that I just described, that can provide warnings for pilots before a collision could happen. And then I can give the joystick to an unexperienced pilot, and I can allow this pilot, this untrained pilot, or a scientist to operate the ROV in a safe way in the environment, because the robot is going to take control when a dangerous situation. You see these arrows that appear. When the blue arrow appears, it's telling what is the direction in which the control system is going to move the robot to counter-effect the command that the pilot is sending. So basically, we see that our omnidirectional vision system is able to provide us with spatial awareness of the environment and avoid these zones that can compromise the safety of the robot. And it allows pilots to collect data without having to worry about collisions. This is very good for scientists, so that then the scientist is just thinking on the coral he wants to map and not the safety of the robot. And of course, this approach is useful not only for ROVs, but also for AUVs in autonomous navigation missions. But here you see a good example with the simulator, how the robot is able to handle these situations. Okay, so let's get to the conclusions. Basically, we've seen in this talk that image pre-processing is essential underwater, because this is what allows us to then do further processing of these images, either for do classification or for building these panoramic views that we have seen. We have seen that we can build really impressive maps, 2D and 3D maps with current state-of-the-art technology, and we have presented this novel payload based on an omnidirectional vision that can be used potentially for teleoperating the robot on a different way than what we have been seeing until now. So this is it for the talk. Thank you very much to everybody, and I hope we can meet in person next time. Take care.